In this video, we're going to talk about two basic counting principles. So counting techniques are used to determine the number of elements in a set without having to enumerate them one by one. So in a lot of situations, if we can describe what's in a set, or we can describe how the set is being built, rather than having to actually make a list of what's in the set and then just count elements one by one, we can determine how many elements are in the set just in general, based on the information we know about how that set is defined. So we're going to look at two different principles that are going to be applied in different situations. One's called the addition principle, and then we'll also have the multiplication principle. So as a way of illustrating what the addition principle is and how it's going to be used, let's look at an example before we actually define the official rule. So for example, suppose that the enrollment in a mathematics class consists of 22 math majors and 16 physics majors, and that 7 of these students have double majored in both subjects. How many students are enrolled in the class? Okay, so notice in this case we have 3 different numbers defined. We have 22 math majors, we have 16 physics majors, and we have 7 students that are double majoring in both of these subjects. So intuitively speaking, if we wanted to know how many students are in this class, well, if we have 22 people who are math majors and 16 people who are physics majors, intuition might say, we'll just take those numbers and add them together. So if we took 22 and added on 16, we'd get 38. This particular answer is actually incorrect. That is not the number of students in this class. Why is this not the number of students in this class? Because we've got 22 math majors and 16 physics majors. We put them together in a class, that's going to be 38, right? No, the problem is we didn't take into account how many people are taking both, how many people are categorized as both math majors and as physics majors at the same time. So these 7 people here, well, they were counted once because they're math majors, and then they were actually counted a second time because they're physics majors. So this total is actually too high because it double counts those double majors. It double counts the individuals that would have fallen into the set of math majors and the set of physics majors. So we're close, but we have to adjust this number to account for this issue with double counting. So if we were to add 22 together with 16, that gives us a total that's too high. We know that those 7 people that are double majors were counted once here. They need to be counted at least once because they are students in the class, but they were counted once here, and then they were counted a second time here. Well, we need to count them once, but we need to make sure we don't count them twice. So if we total up the math majors and the physics majors, but then subtract the 7 that we know have been double counted, then we're making sure we only count those 7 students one time. So 22 plus 16 gives us the 38, and then we subtract 7, and that's going to give us 31. So 31 is going to be the actual total in this class. That's going to be the idea behind the addition principle, this idea of we can't just add up what's in 2 sets if there's overlap between the 2 sets. So more generally speaking, and in terms of the notation that we introduced when we talked about sets, the addition principle states that for any sets A and B, the number of elements in A union B, in other words, in A or in B, in this case it was math majors or physics majors, it's going to be the number of elements in set A plus the number of elements in set B, not surprising, but as with this situation, remember that double counts anyone who's in both A and B at the same time. They're counted once here, they're counted once here. So we also have to subtract the number of elements in the intersection, the number of elements in the overlap. That way they're counted one time here, and then when they're counted the second time here, we negate that and we reverse that and we end up with the correct total. So let's look at another example that's a little bit more involved. So a city has 2 daily newspapers, the Sentinel and the Journal. The following information was obtained from a survey of 100 city residents. So 35 people subscribe to the Sentinel, 60 people subscribe to the Journal, and 20 subscribe to both papers. So our goal here is to draw a Venn diagram to represent this situation and then answer a few questions about the situation using this diagram. Now, how does the addition of principal apply in this situation? If we were to determine how many subscribers are there to either journal across the city, we might say take the 35 Sentinel subscribers, take the 60 Journal subscribers, and then just add them together. What's the problem with that? Well, remember, there are 20 people who subscribe to both papers. So 20 subscribe to the Sentinel, so 20 of those are included here. And then that 20 is also included in terms of those 60 Journal subscribers. So if we were to just add up the 35 and the 60, that's double counting those 20 individuals because they fall under both of those categories. They subscribe to both journals. So the addition principle would tell us if we wanted to take the total, determine how many subscribers there are across the city, then we can't just count 35 plus 60. We have to subtract that 20 to make sure that it's not double counted. So that's essentially the gist of the addition principle. Now here's how we're going to use this idea in a slightly different way. We want to draw a Venn diagram representing subscriptions. So either subscriptions to the Sentinel or subscriptions to the Journal. So we're going to think of those as the two sets that we're further grouping people into. Now we need to think about, number one, what does the universal set represent? In this case, we took a survey of 100 people, and then based on how they answered, we categorized them into a couple different sets. So our universal set is going to be the people that were surveyed. Those are the people that are then being categorized into the sets. We can't say that the universal set is everyone in the city because we can't categorize everyone in the city. The only people we know things about are these 100 people that were surveyed. So the universal set has 100 elements in it. It's going to be the 100 people who were surveyed. So we know in total, in terms of different regions in our Venn diagram, we have 100 people represented among those 4 regions in our diagram. Now we're going to define our first set with the letter S, S for Sentinel, and then the letter J for Journal. If we want to determine who falls where into this diagram, or more specifically, how many people fall into particular regions, we're going to start with the intersection. Anytime you want to do a Venn diagram and you want to label the different regions, you're going to start with the intersection. So in this case, this is S intersected with J. Well, what do we know about anyone who falls into that intersection? We know, number one, they subscribe to the Sentinel, but they also subscribe to the Journal because they fall into both of those circles. So those are going to be the individuals who said that they subscribe to both newspapers. Now we were told that 20 people subscribe to both papers, which is why we have 20 in the intersection. So that means the number of elements in S intersect J, we would describe that as the intersection of these two sets. The number is going to be 20. Now we build outward from there. So we always start in the very middle of the diagram, there in the intersection between our two sets, and then we're going to go outwards from there. So we need to know who falls into the rest of circle S and who falls into the rest of circle J. This is where we go back to the numbers we were given. So the total number of people who subscribed to the Sentinel was 35. So they surveyed 100 people, 35 people said, yes, I subscribe to the Sentinel. Maybe they subscribe to the Journal as well, but we just know 35 people in total subscribe to the Sentinel. Well, when we label that region of the diagram, we do have to take into account who was already counted. So 20 people, the ones who subscribed to both papers, 20 people had already been categorized. Now those 20 people are also counted among the 35. 35 is a total, 35, and then 20 of them subscribe to both. So when we label the region that's just in circle S but not in circle J, we have to take the 35 total and we have to subtract the 20 that were already counted. So 35 minus 20 is going to give us 15. So 15 people fall into circle S but not into circle J. Now we need to do the same thing on the other side. So we counted 20 people who subscribe to both journals. We know in total the number of Journal subscribers is 60. 20 of them were counted, so the remaining are 60 minus 20, 40 individuals. So 40 in this particular region only in circle J, but not in circle S. Now it seems like we're done, but we're not quite done. There's still one more region in the diagram. So there's the innermost section, the overlap between the two circles. There's the two regions where someone falls into one circle or the other, but not both. There's also the region of the universal set that's outside of the circles. What can we say about someone in this external region? They were surveyed, but they weren't categorized further into one of these sets, the S set or the J set. Well, how do we know who would fall there and how many individuals fall there? We have to go back to the entire total. The entire total in this situation was 100, where 100 people were surveyed. We've taken some of those individuals and we've categorized them a little bit further based on the fact that they said, yes, I subscribe to this magazine, yes, I subscribe to this one, or newspapers. So we have to subtract all of the individuals we've already counted. Now again, we're going to have to be careful here. We're not taking 100 and subtracting 35 and 60 and 20. Imagine doing that. If you do that, you're actually going to end up with a negative number. So negative number of people, a negative count of people, that doesn't make any sense. When we subtract from the total, we're subtracting the regions we've already labeled, because the 15, the 20, and the 40, those have all been grouped into separate categories at this point. So when we subtract from the total, we're subtracting each of the values within those specific distinct regions. So 100 minus 15 minus 20 minus 40, and that's going to give us 25. So 15, 20, and 40, and then the external region, everything that's in the universal set but not further grouped, there are going to be 25 elements there. Well, based on this labeling, let's answer a couple of questions. So the first question is, how many people subscribe to the Sentinel but not the Journal? Well, where would we find this in our diagram? They subscribe to the Sentinel, so they fall into the set S, but not the Journal. Anytime you see that word not, think complement. We're taking journal complement, which means delete the circle for the Journal. Okay. So they subscribe to the Sentinel, they fall into the Sentinel circle, but not the Journal, which means we're not considering the people that would overlap. So that's going to be 15. We have 15 people that subscribe to the Sentinel, but don't also subscribe to the Journal. We'll say we want to flip that. How many people subscribe to the Journal, but not the Sentinel? In other words, they fall into the Journal circle, but not the Sentinel circle. Well, there's going to be 40 people that fall into that region, so 40 subscribers like that. And then the last question is, how many people do not subscribe to either paper? In other words, get rid of the Sentinel circle, get rid of the Journal circle at the same time. Who's left? Well, in this case, 25 people were left. So anyone who was further grouped had to have subscribed to one of the newspapers. Anyone who's in that external region in the universal set but not further categorized, that's going to be someone who took the survey, so they're in the universal set, but they didn't subscribe to the Sentinel, they didn't subscribe to the Journal, they certainly didn't subscribe to both. That means they subscribed to neither, and that's going to be 25 individuals. Now we can also organize this into a table form. Depending on just categorizing people into very specific sets, we can put this into a table form based on what we can see. So subscribers to the Sentinel, we know there's a total of 35 there. Subscribers to the Journal, we know there's a total of 60 there. So 20 people subscribe to both. And then those individual values, 15 and 40, remember those were the values that were in individual circles, but not in the overlap. So they subscribe to the Journal, but they don't subscribe to the Sentinel. That would be 40 individuals. They subscribe to the Sentinel, but don't subscribe to the Journal. That was 15. And again, notice those totals. So 20 and 15 adds up to the 35 total Sentinel subscribers. And then 20 and 40 add up to the total Journal subscribers. Now, if they don't subscribe to the Sentinel and they don't subscribe to the Journal, those were the people on the outside in the Venn diagram, so that was 25 left over. So all of these totals add up to a total of 100. So 100 totaled from the rows, and then 100 totaled from those two columns. So that's going to be another representation we can have. Just a different way of organizing the same information. Notice in some ways, the Venn diagram is a little bit cleaner. We can represent a lot of situations and a lot of different categorizations in that Venn diagram without needing to reference so many different numbers at the same time. But this is just another representation we might use. So that's going to be the addition principle. So to summarize that, it just tells us if we want to take the number of elements in a union, we can't just add up the number of elements in each set. We have to account for any overlap. Individuals or individual elements in that overlap end up being counted twice, one in each of the two counts. So we have to subtract the intersection one time in order to account for that overlapping region. Now let's look at the multiplication principle. We're going to use this a little bit more from here on out, but both principles are going to be important in different situations. So again, before we introduce the formal principle, let's look at an example to put things in a little bit of context. So a store stocks jackets in small, medium, large, and extra large. All are available in red or blue. What are the combined choices and how many different choices in total are there? What I have here is called a tree diagram. A tree diagram allows us to organize all different combinations. So what's going on here? Well, we have jackets in different sizes and different colors. So we have to take into account that each size can then be made in one of two colors. So in order to organize all the different combinations, we can create a diagram like this, and it's going to allow us to explore all the different possible combinations. So we're representing our stock. If we go just sizes, think of options. We have 4 options for size. So we could choose a small, we could choose a medium, a large, or an extra large. So automatically that puts us into 4 categories. We make one choice. Choice 1 is choose a size. Well, each of those sizes then comes in one of 2 colors. So our small could be red or blue. We have 2 options there. Our medium could be red or blue. We have 2 options there. Our large could be red or blue, and then our extra large could also be red or blue. Once we get down to the very end, imagine tracing each path. So if we started here and traced the first path, that would be choosing a small that's red. Now if we trace the second path below that, that would be a small that's blue. So 2 possibilities are associated with choosing a small. We can choose a small red, we can choose a small blue. So that's going to be 2 total choices. We could choose a medium red, or we could choose a medium blue. That's 2 more choices, so we've got 4 so far. And then we could choose a large red, a large blue, that's 2 more choices, or an extra large red, an extra large blue. In total, we have 8 different combinations, 8 different possible combinations for how we could choose a size, and then how we could choose a color to go with that size. So that essentially means if you think in terms of SKUs, stocking different items, there's potentially 8 different SKUs for this particular type of item that this store sells. So this summarizes what we're doing in the multiplication principle. What's actually happening here? What's happening is we're making a sequence of choices. So our first choice is choosing a size. Our second choice is from that size choice, now we have to choose the color we want. So think about how many ways we had to choose for our first choice. We had 4 sizes, so we had 4 different options for our choices. The next choice we had to make was color. We had 2 colors, so we had 2 additional colors. Now notice the total we ended up with. We ended up with 8. Well, if we have 4 choices for our first option, or 4 options for our first choice, I should say, and then 2 options for our second choice, imagine multiplying those. 4 options times 2 options gives us 8 choices in total. That's not a coincidence. That is the multiplication principle. If we're going to perform a sequence of operations, multiply together the number of ways we do each step. And it's completely generalizable. So if we were to do n operations, that's just generic, n, just a counting number. We could do 5, we could do 10, we could do as many operations as we want. In other words, think of those as steps in a process. So step 1 is choose your size. Step 2 is choose your color. So we're going to define those as O sub 1, O sub 2, all the way up to O sub n. So those are the actual physical defined steps we're taking. We can perform them in any order. The order does not matter. 4 times 2 is 8. 2 times 4 is 8 as well. So order's not going to matter. And then suppose for each of these operations, there's a certain number of possible outcomes, different ways that that could go. That's going to be the 4 and the 2. So we're going to call those capital N sub 1, capital N sub 2, and capital N sub n. Okay, these are going to be the number of ways we can perform each step. Then the total number of possible outcomes, all the different combinations, different ways we can assign a size and a color in order to create one jacket, one SKU, is going to be the product of the number of ways we can do each step. So in other words, identify the process. Think about the steps in the process. What are you doing at each individual step? Well, how many ways are there to accomplish each step? Once we know what the steps are and how many ways there are to accomplish each step, we take the number of ways we can do each step and we multiply all those values together. That's going to give us the total number of combinations. What we're going to find with these kind of problems is that the numbers get surprisingly big, surprisingly quickly. So the number of ways to perform, for instance, a 5-step operation, maybe there's 3 or 4 ways to do each step. It's typically kind of surprising how many different total combinations there are in those situations. So let's look at a few examples. So first example, a college is using a 5-question screening test for admission to a particular program. The computer stores 5 comparable questions for the first test question, 8 for the second, 6 for the third, 5 for the fourth, and 10 for the fifth. What we want to know is how many different 5-question tests can the computer select. So the computer is making a test, okay? It's making a test. It's going to assign 5 questions per test, but tests are going to be different. So for the first question, the computer can choose from 5 different comparable questions that test the same concept. For the second question, the computer can choose from 8 different possibilities. For the third, it can choose from 6. For the fourth, it can choose from 5 options. And then for the fifth, it can choose from 10 options. So it's going to take each of those questions and then it's going to choose one of the options for that question. So we need to start by thinking about what's the process? What are the steps in this process? What are the operations? Well, the actual physical actions, operations that are taking place are the choices of questions. So in this case, because the computer's choosing 5 different questions, there's 5 steps in this process. So operation 1 is choose question 1. Operation 2, choose question 2, all the way down to the last operation, operation 5, which is choose question 5. Now, because we have different information stored for each of these questions, there's a different number of ways to accomplish each step in the process. So for the first test question, there's 5 options that the computer can choose from. So if operation 1 is choose question 1, then n sub 1 is going to be 5. That's the number of ways we can perform that step. Now for the second question, there's 8 options. So n sub 2 is going to be 8. For the third question, there's 6 options. So n sub 3 is going to be 6. For the fourth question, there's 5 options. So n sub 4 is going to be 5. And then for the final question, there's going to be 10 options. So n sub 5 is going to be 10. The computer performs these 5 steps, and there's this many ways to do each of those individual steps. So the multiplication principle says if we want the computer to pick the entire test, in other words, do all 5 steps, pick all 5 questions, we're going to multiply together the number of ways we can do each of those steps. So 5 times 8 times 6 times 5 times 10. And notice we don't even have that many choices for each individual question. But when we take those and take their product, just to prove that that answer is actually correct, 5 times 8 times 6 times 5 times 10. And sure enough, it comes out to 12,000. Just based on that small selection, we can come out with 12,000 different tests, which is, again, surprisingly high. But in a situation like this, if we're talking about admissions, we're trying to prevent cheating, this means we have 12,000 different tests that the computer can make, and having that many options, of course, is going to lessen the possibilities that students are going to cheat on something like this. So that's the general idea behind the multiplication principle. What's the sequence of operations? How many ways can you do each operation? Take the product of all those number of ways. Now let's look at another example, and we're going to impose some additional restrictions. So sometimes we can define the sequence of steps, but there are limitations towards how we can do each step, just depending on how the situation is defined. So here's the question. How many 3-letter code words, so we're choosing a sequence of 3 letters, can be chosen from the first 8 letters of the alphabet under each of the given conditions? Okay, so we have 3 different conditions that are going to impose restrictions on how we can make these choices. Now notice we're only choosing from the first 8 letters of the alphabet, so not the whole alphabet, just the first 8. So A, B, C, D, E, F, G, H. Okay, so all the letters from A to H. So we're choosing 3 letters. That means there's 3 steps in this process. What are they? Well, option 1 or operation 1 is choose letter 1. Operation 2 is choose letter 2. Operation 3 is choose letter 3. We're making each of those individual choices. Now we're going to impose some further conditions on how these letters can be chosen, and that's going to impact the total number of combinations we can get. So situation 1, no letter can be repeated. In other words, once we choose a letter, we check it off the list and we can't use it again. So our sequence of operations is the same, but now we need to determine how many ways can we do each operation. So start with letter 1. We're choosing letter 1. Well, we're choosing from the first 8 letters of the alphabet, so we have 8 ways to do step 1. So we have 8 letters to choose from, 8 ways to do step 1. Now, when we go to step 2, we're choosing letter 2. We've been told that we can't repeat any letters. So when we did step 1, we used up one of those 8 letters. Well, how many are left? In this case, there's 7 letters left. So for our second letter, now we only have 7 to choose from. Whichever one we already used, we can't use. We don't know which one was used. Notice in this case, that doesn't actually matter. All we know is that one of them was used, and we can't reuse whatever that letter was. So we go from 8 options to 7 options. Now with the third and final letter, we've chosen 2 letters already. So whatever those 2 letters are, those are already taken, which leaves us 6 left to choose from. So our final operation, there's 6 ways to accomplish that particular step. So we take the product of each of those ways we can perform each step. So 8 times 7 times 6, and that's going to give us a total of 336 different possible combinations. So 336 code words. Now let's change the situation. What if letters can be repeated? In other words, it's possible to have a code word that has all the same letter, or maybe one letter just repeats one time, something like that. We can repeat. So there are no limitations on how we can choose, aside from the fact that we only have this small pool of letters to choose from. The operations don't change. We're still choosing 3 letters, but notice what's going to happen to the number of ways we can perform each step. So operation 1 is choose letter 1. We have 8 letters to choose from, so 8 ways to do that step. Operation 2, choosing our second letter. Letters can be repeated, which means whatever letter we chose for letter 1 has now been thrown back into the pool, and we can use it again. So we still have 8 options for letter 2. We didn't decrease the number of options because we can repeat letters if we want to. And then letter 3, again, we throw it back into the pool, whatever we chose for these 2, so we still have 8 options. So in this case, the number of ways we can do each step is actually going to be the same. So 8 times 8 times 8, we can use an exponent here if we want. So 8 multiplied 3 times is going to be 8 cubed, which is going to be a total of 512 code words. Now, why did this number end up being higher? It actually makes sense that it ends up being higher. In general, the more specific restrictions you impose, the fewer possible situations will meet those restrictions. In this case, we didn't have any restrictions above and beyond just our small pool of letters. So the fewer restrictions there are, the more possible outcomes. The more restrictions there are, the fewer possible outcomes. In other words, the stricter the situation, the less likely we are to choose something that satisfies those requirements. Okay, let's look at one final one. Adjacent letters cannot be alike. So we can have some repeats, but we can't have an A and an A back to back. We could have maybe an ABA, but we can't have an AAB or an ABB, something like that. We can't use the same letter back to back. Okay, so our operations again have not changed. We're still choosing letters, but how many ways can we do each operation? For letter 1, we still have the 8 choices, no restrictions yet. We can choose from the whole pool. Now what happens when we get to letter 2? We can't choose whatever letter we just chose, so that decreases our options by 1. So for operation 2, we have 7 choices. Now here's where there's a little bit of a leap once we get to option 3. I want you to think about what's happened. We chose a letter for letter 1. Once we got to letter 2, we know we can't use that letter, so we chose a different letter for letter 2. Now once we get to letter 3, we can't match letter 2 because those are adjacent. But what about letter 1? Well, letter 1 is not adjacent to letter 3. So whatever letter we chose for our first one, we can throw that back into the pool. We don't have any issues with that letter because it's not going to be a letter adjacent to the current one we're choosing. So although we can't choose whatever matches our second step, we now have the ability to choose whatever letter we chose in the first step, again, because of that requirement for adjacency. So for operation 3, there are also 7 choices. It's just not the same 7 choices as we had above. Whatever letter we chose for option 2, for operation 2, we can't use that now, but we can throw back in the letter that we used the first time as another possibility. So 8 and then 7 and then 7. So that's going to give us a total of 392 outcomes. So this is just a small sampling of the kind of problems we're going to encounter. Again, we're going to use these kinds of counting techniques in the context of probability. How many ways can we perform a particular operation? How many combinations meet the requirements we have? Those are going to be the contributing factors to our probabilities.